objectives continuing to not cooperate. So today we'll look at conditional random fields again, and using a different set of notations, one that I think is easier to think about when you think about implementing things in more general form, and then I'll provide a brief overview of general structure prediction. But first, we're going to talk about some conceptual connections in comparing and contrasting naive Bayes versus logistic regression, and these conceptual comparisons will generalize to sequential models such as hidden Markov models versus conditional random fields. There were a number of questions about conditional random fields versus hidden Markov models in the previous lecture, and I figured this sort of comparison will help clarify some of those questions. And so just to recall, a naive Bayes model, if you take the graphical model representation, it looks like this. And the basic idea is that it models the joint distribution of a single y, so the data is a single y and a vector of x's. And it models the joint distribution of the x, y pairs as this multiplicative form, which is essentially a conditional independence assumption, the naive conditional independence assumption, where we have a prior probability of a label and the probability that this label generates each of the feature values. Okay? Logistic regression, on the other hand, and again, I'm using this sort of a notation I'll try to unify later, says, well, okay, I'm only going to model the probability of the label given the feature vector x, which is input. So, and this is done so because typically in most prediction tasks, we just care about predicting y, or in this case, predicting the distribution of y conditioned on the input x. And the way that works is you have some scoring function, which I generically call f, capital F, over inputs and outputs. And the conditional probability is modeled by e to the f of the scoring function of the xy pair, which you're modeling, that you're computing the probability over, divided by the sum over all possible values of the y. So here, if there's capital L values, the index k indexes over all. Right? So this is the standard form. This is the most abstract form of logistic regression. And in the case of standard linear logistic regression, this F scoring rule is just the linear scoring rule. Okay? And the way you can think about it abstractly is that, let's say this is your scoring rule, this F, which is defined as this for the standard logistic regression. As the scoring rule increases, then the probability of that y, given this x corresponding, goes up, like this S-shaped curve, and this is the logistic shape. So when we compare naive Bayes with logistic regression, they both actually have the same number of parameters, right? Naive Bayes has L parameters. L is the number of the values that the y can take for the prior distribution P of y. Logistic regression is L values for one for each bias term. Right? Naive Bayes has L times D parameters, where D is the number of values in X, features in X, also known as the observation matrix. Logistic regression is also the same number of parameters. I mean, these things can go up or down depending exactly how you sort of formulate it, but the basic idea here is that they have the same order magnitude number of parameters, and so the question is, okay, they more or less have the same model complexity. What are they trying to model? Naive Bayes is trying to use that model complexity to model the joint distribution. Logistic regression uses the same model complexity to model only the conditional distribution. So let's try to interpret the parameters of logistic regression. The interpretation of the parameters of naive Bayes is very trivial because each individual parameter corresponds to a single probability table, right? And probability tables are, by definition, very easy to interpret. So in naive Bayes, the joint distribution looks like this, where I'm using the matrix notation for simplicity, representation of compactness. And every single parameter within this matrix notation, every single parameter explicitly corresponds to some probability, right? That's the definition of the naive Bayes and also hidden Markov model construction. On the other hand, logistic regression, every single parameter does not necessarily correspond to some probability in a clean way, right? So if we just look at the exponent, the numerator of the logistic regression function, probability function, it's this guy, right? So, and if you look at this guy is actually Given an x, the denominator is constant, right? Because it sums over all possible y values, y equals k, right? And so the denominator is constant. So we could say that the probability of a specific y, given an x, conditioned on an x, is proportional to the numerator, right? Because the denominator is constant. Okay. This is a sum. So this is a dot product, and this is a subtraction. So this is essentially a sum inside an exponent. So I could actually make it into a product of the individual terms, right? So I'm just rewriting this as instead of a e to the sum, a product of the e to the terms, right? Okay, maybe I'll just rename the parameters, right? Maybe I'll rename this parameter A. I'll rename this parameter O. Okay, it looks a lot like, the structure of this parameter looks a lot like this, right? Subject to an exponential transform, which is monotonic and one-to-one. And so, subject to an exponential transform, it basically looks like the structure of this, right? It seems like there's a one-to-one correspondence between the parameters in logistic regression and the parameters in naive Bayes. Right, they look very similar. And this was sort of buried, and this confusion was buried in several questions that were asked in the previous lecture about the relationship between hidden Markov models and conditional random fields. Okay. So can we just interpret these as the conditional probabilities? Well, we cannot, because just this interpretation of just this observation of the connection ignores the denominator, right? It ignores the denominator in the logistic regression case. We say that it's proportional to, and the fact that it's proportional to and has this structure is one of the ways that logistic regression is computationally convenient. However, you cannot ignore that. You cannot take this interpretation literally as connecting this to this exactly, because you cannot ignore the denominator. And so here's how it would work if we sort of flip it around and we're trying to model exactly p of y given x, right? In logistic regression, it's just this, with some renaming of parameters, right? So here I just rename parameters. In naive Bayes, I have to take my joint distribution and divide by p of x, right, via the law of conditional probabilities, right? And the p of x is just simply p of x comma y, where y sums over all possible values of y indexed by k, right? And that looks like this, right? Okay, they still look pretty similar, right? Because this summation is the same in the denominator. This term corresponds to this term. And these terms correspond to these terms. They still look very similar, right? So maybe the interpretation still holds. However, in naive Bayes, because we're modeling a joint distribution, each of these terms are constrained to be no greater than 1, between 0 and 1. Right? There's no reason you need that for logistic regression. Right? There's no probabilistic interpretation, direct probabilistic interpretation of the parameters of logistic regression. So in logistic regression, this value can be, 500, right? And then this term would be e to the 500, which would be huge. Whereas the corresponding term in naive Bayes is bounded between 0 and 1, because you're trying to model the joint distribution. And because we're only trying to model the conditional distribution of logistic regression, we don't care. We just want to fit the parameters to maximize this, to maximize the fit of this on training data as well as possible. In the naive Bayes, that's not what we care about. We care about fitting this as well as possible. And because of that restriction, we have a restriction here. And this is one of the key sort of points in comparing and contrasting logistic regression with naive Bayes that lifts to the sequential setting where you compare and contrast conditional random fields with hidden Markov models. So it's important to sort of see the difference here, and see how this is a more limiting model class if this is what you care about. Okay, now let's talk about training, right? So there's another connection we can compare and contrast in terms of the optimality conditions of the training procedure. In naive Bayes, we're trying to maximize the likelihood of the joint likelihood of the training data, right? The probability. So assuming each training example was sampled independently from the test distribution, we maximize the likelihood of our approximation of the test distribution, we maximize the independent probabilities of the input-output pairs under our joint probabilistic model of naive Bayes. Of course, the negative log is a monotonic transform, so this is so finding the parameters that maximize this is equivalent to finding the parameters that minimize this. And of course, this has this structure. So I'm going to do a little bit of reparameterization. So if we want to estimate the parameter p of x given y for, let's say, some x's and just one of the x's, right? Then it equals an entry in this observation matrix, which, as you know, has to be normalized sum to 1 over all the x's. So I could just reparameterize it like this. That should be a comma y. Okay. So recall that in supervised training, just from this slide, I want to find the parameterizations of my model to minimize this loss function essentially. And we're just going to look at the part that contains this component. So that's just this component right here. Right? And if you take the gradient, and we talked about this last week, but if you take the gradient of just this term, right, and you extract out this term from this, so you get this, right? It's the number of times you get that it's equal to negative the number of times you observe x comma y divided by your parameterization, curve parameterization plus this, right? And you could work out the derivation yourself, but the punchline is that if I set this gradient to 0, which is a necessary condition for optimality, then I move this, and I move, let's say, this to the side, divide by this, move this to the side, divide by this, multiply by this, and I get this, right? What does that mean? Well, keep in mind that this is the probability, right? It's just a reparameterization, so this is the probability. So we get that at optimality, right? At optimality, we get that we want to match what our model said, sorry, tongue twister, not actually. So our model says that the probability of x given y is equal to some parameter. At optimality, that probability needs to match the empirical probability of our training set. That is a necessary consequence of the optimality condition of training in naive Bayes model. The optimal solution to this optimization problem requires that this condition be satisfied. If we're not doing regularization, so we're not talking about regularization. Ignoring regularization, this is a necessary consequence of the optimality condition of training in naive Bayes model. That whatever components of the model however we break up the independence, property nuggets of the model in a naive Bayes, and in naive Bayes, it's this guy times p of y, right? However we break it up, when we just look at those tables, the tables need to match the empirical distribution. Okay, now let's look at training for logistic regression. In logistic regression, we minimize the log loss, which is negative log of the conditional probability, which I can expand out like this, using the definition of the probability, and the definition of f, in the simplest case, is just a linear scoring function. Okay, and here's the gradient. I'm skipping the derivation. I showed the derivation in the second week of lecture. You could drive it yourself. Just take the derivative with respect to one of these parameters. You get something that looks like this. And this part, for the linear scoring rule, is just x. I keep it general like this because for conditional random fields and more complicated logistic models, this can be something a little bit more complicated. But in the standard linear logistic regression, it's just x. Okay, so let's try to interpret this optimality condition. Right, this is the gradient. If I set the gradient to 0, which again is a necessary condition for optimality, what does this equation reveal if I set this gradient to 0? Well, okay, so I set the gradient to 0, so 0 equals this guy. So now I can shift things over to the left-hand side. I can divide by this because it's divided this though I can divide by this because it's set equal to 0. So I get this, right? This is basically the number of times in the training data that I observe a label yi equals y, right? This summation. So what does it say? This says that at optimality, it must be the case under my logistic regression model that the sum of that the frequency of observing the label y matches the predicted frequency. This is a necessary condition implied by the optimality of training a logistic regression on maximizing the conditional likelihood on the data. Is that a question?
Yeah, how did you divide by dfxi? It seems like the factors in the sum. Because it has the same instance as I.
Yeah, it's a different x rate. Because it would be xi.
Oh, right. Sorry. Sorry, you're right. I'll fix it. It's a small typo. The empirical frequency of the feature should match the predicted feature, the empirical frequency of the feature.
Like for linear model, there'd just be xi's and all those, right?
Yes, small typo on my part. But the point is that there's a small typo on the side. So there should be, the xi should remain. I guess my point is that the empirical frequency on the training set needs to match the predicted frequency according to our model. That is a necessary condition implied by the optimality conditions of logistic regression. And these optimality conditions are consequences. These optimality conditions are consequences, again, the same errors on this slide. I'll fix it after class. The same consequences are, these optimality conditions are consequences of the fact that under the naive basis assumption, we're maximizing the joint likelihood of the data. Under logistic regression, we're trying to maximize the conditional likelihood, right? And therefore, the empirical probability, certain empirical probabilities must match the predicted probabilities according to our model over the data. Right? And by matching that, that's when we maximize the likelihood of the probability of our model on the data. And because the models are different, maximizing them will imply different trade-offs given the same model capacity. And that is why logistic regression tends to perform better if this is the only thing you care about, predicting y values. And then you can do the same argument for CRs and HMMs, just lift it to the situation case. So any questions on that comparison between naive Bayes and logistic regression? Okay, a few people also had some more questions about the connection between generative and discriminative models, like why you would use one over the other. So just a brief sort of review of that. In a generative model, we're modeling the joint distribution, so we care about modeling both x and y. We care about everything. In a discriminative model, we only care about the probability of y given x. Sometimes it's not even a probabilistic model, like an SVM, right? So examples include naive Bayes and HMMs, CRS. Other types of generative models, like topic models, I briefly overviewed that last week. SVM, least-squares are other types of discriminative models that are not necessarily probabilistic. Trained via maximum likelihood, you train via, if it's a probabilistic model, you train via maximum conditional likelihood, which is equivalent to minimizing the log loss. Of course, we could also, if we take the loss minimization interpretation, we could also minimize some other loss functions instead. These are all discriminative models. Generative models are always probabilistic, as far as I know. I guess I can't imagine generative models that are not probabilistic, but by and large in the literature, predominantly, generative models are probabilistic. In the literature, discriminative models are often not probabilistic. Like an SVM does not have a direct probabilistic interpretation. in order to keep the model very tractable while modeling joint distribution, you often have to make very strong independence assumptions. Right? Logistic regression, for example, can make more flexible assumptions because it's only focused on modeling Q, Y, given X. Because the most common use case of these models is to predict Y given X, the way you train a generative model gives you a mismatch between the training task, the training goal, and the prediction goal, because you have to use Bayes' rule as a consequence. Whereas in discriminative models, you're training to directly optimize the prediction goal. Of course, on the other hand, generative models can sample, is a model of the test distribution, so you can generate samples for the test distribution under your model. So you can sample anything. Discriminative models can only sample Y given X. You cannot sample X comma Y. And if you look at sort of the comparison of the parameters, right, the parameters of the logistic regression model do not correspond to individual probabilities. They're not normalized probability. And so you can't just use them in isolation as a probability. And also because you have a joint distribution, if you have missing values in the X, and you want to predict Y given X with missing values, you can just marginalize out over the missing values. You cannot do that in the script. Yeah.
Can you give any examples off the top of your head where a generative model is more useful for a problem than a discriminative model?
If you often expect missing values, I mean, there are many examples where there's lots of missing values, right?
So that you just can't, basically use the discriminative model if you can, and then...
Well, with discriminative models, you can, there are things you can do to try to get around it, but it's not natural. I mean, it can be hacky. Like if you're trying to do re-identification of the same person, like you have like cameras, often come up with these types of surveillance-based examples, but if you have like multiple cameras in a building, and then you have this some person you're trying to track, and you only track them for a small window of time, they walk around the building, you want to recover their path, there's lots of missing value there. They may or may not appear on the camera. Right? And you want to build a probability distribution over that. This is one example.
Yeah.
If you want to make like an automated detective, right? You observe some value, you make deductions about other values, right? That's what detectives, like people who do these things do. You can't do that with a discriminative model, like one of your X's is missing. Right? You want to be able to ask questions about distributions of any. You want to be able to treat any of your variables as the Y, and any of the other variables as the X. Right? So generative models, at a high level, they don't make a distinction between X and Y, although sometimes in the structural assumptions they do. Okay, so now let's move on to sequence prediction CRFs. Just to recap, the goal is to predict X, get a sequence of Y's given a sequence of X's. The Y's typically fall into a very small label space. So here the label space is 6. And so these are just examples. We talked about that before. This is a first order sequence model in conditional random field notation. So the idea is want to model a probability of an entire sequence Y given an input sequence X in the following form. Right? And if I reinterpret these parameters as a scoring function, like f of Y given X, or sometimes I write this f of X given Y, it doesn't really matter, then I can model the probability of a sequence in this form, where Z sums over the scoring rule over all possible sequences that can of the same length as the input sequence. So recall that if f of x, y, if y was just a single sort of variable, and if f of xi was just a linear scoring rule over the x, you get standard logistic regression. If y is a sequence and you get this summation scoring rule, which is still linear in the model parameters, you get conditional random fields. Yeah.
Sorry, could you repeat that?
Just what I just said?
Yeah.
Okay, sure. So, if you probably easier. Yeah. So, I should have thought of this. Okay, so I'm just going to focus on this equation for logistic regression. So, I have some scoring rule that is a summation over my parameters times, that is a linear function over my parameters, right? By linear, I just mean it's a sum over my parameters times some coefficient, where the coefficient is given by the input features x. So logistic regression, if I take this interpretation, logistic regression is just the p of any y given some input x is a linear scoring rule f of x comma y defined with some linear formula divided by the summation over all possible values that y could take. In the case of multi-class logistic regression, y can just take L values, and I sum over all the scores. This is logistic regression. Conditional random fields. Conditional random fields look like this, right? Where we have a sum over the score that associates a token with the input, with the output token with the input token, and a score that associates a transition between the previous token and the next token, right? But this is still a linear square root because it's a summation over the model parameters, multiply a coefficient, the coefficient here are just 1 or 0, right? And so I could also write this as an f, right? F of x, y, where y is now a sequence of sequence of outputs, instead of in the standard logistic regression, which is a single output, looks like this. The parameter notation is different, but again, the thing you need to keep in mind is that it's just a linear sum over parameters. Right? So then it looks like this again, where the z sums over all possible sequences of y prime of the same length as your input sequence x. So if I just define a linear scoring rule over my parameters, if y is just a single variable I'm predicting, with the appropriate square rule, this is logistic regression that we've seen before. If y is a sequence with an appropriate linear scoring rule for my parameters, this is conditional random fields. That's all I'm trying to say.
Thanks.
Of course, this is very hard to compute naively because there's an exponential. The number of y primes here in the sum grows exponentially with the length of x. We deal with that using various algorithms like four-factor algorithms. As an example, we did this example yesterday, or on Tuesday. Imagine that I already have a pre-trained model, so we'll talk about training there. And the input is fish sleep, and the y that we're considering is noun, comma, verb. And there's only two possible tokens in this example, noun and verb, and only two possible words, fish and sleep, in our vocabulary. Okay, so the probability of this y, noun given verb, is equal to the summation of the corresponding tokens in our corresponding values in these parameter matrices that corresponds to noun transitioning to start transitioning to noun, noun associating with fish, noun transitioning to verb, and verb being associated with sleep. You sum that up, you get e to the 4. And then you divide by summing over all possible sequences of length 2 of noun, verb, verb, noun, etc. And there's 4 such possibilities. So in a simple example, I can just exhaustively compute all 4, and you get about 0.6, 60%. So if this is our scoring rule, and I hold all the other parameters fixed and I increase the score, the total score of these 4 parameters, then the probability of this sequence, noun, verb, given fish sleep, behaves like this S3. Okay, so now I'm going to introduce some new notation of conditional random fields. This notation is motivated by the fact that conditional random fields are sequential versions, is a sequential version of basic logistic regression. The previous notation that we talked about in the previous lecture was motivated from the interpretation of conditional random fields as a logistic regression version of hidden, conditional version of hidden Markov models. What does that mean? Here's what it means, right? In logistic regression, we talk about feature vectors. We talk about a scoring function, a linear scoring function over feature vectors. And that's how we use to compute a score, and we exponentiate that score and normalize it in order to compute conditional probabilities, right? So we could do the same thing in conditional random fields. We could just define a bunch of feature vectors that is mathematically equivalent to the notation we saw on Tuesday. And given that feature vector, now we're just learning a linear scoring rule in some feature space. So here's how it works. So first let's define a feature vector that corresponds to associating, so this is just a little bit of notation. So this is phi of some token. So A is noun, verb, determiner, one of those. And X is the entire input sequence of words. And it's just an indicator feature, right? This feature, the first feature is 1 if the input token is noun and the jth word is fish. The next feature, the second feature, otherwise it's 0. The second feature is 1 if the input token is noun and the jth word in this sequence is sleep. The third, otherwise it's 0. The third feature is 1 if and only if the input token is verb and the jth word is fish. The last feature in this feature vector is 1 if and only if the input token is verb and the jth word is sleep. So exactly one of the, or given our limited vocabulary and our limited token space, exactly one of these features will be 1, the rest will be 0. So for example, for this feature for a feature map, for the feature map now to fish sleep for the first token, you get this. Because A equals noun, X is fish sleep. We're looking at the first token in the sequence. So the first one is true, and the rest are all false. If we instead say, what about a feature representation of the second token being noun, given the input fish sleep? Well, exactly. So only the second feature is going to be true, and the other ones are going to be false. So the second one's 1, and the rest are 0. And then you can all possibilities. So if you think of our parameter matrix and we somehow flatten it, right? This is just an indexing into one of the entries in that in a flat parameter matrix. That's one way to think about it. So the top two, just correspond to noun class features, and the bottom two correspond to verb class features in this simple